So this is pre-calculus, Apex 4.2. We're still talking about exponents. So 4 to the 6th times 4 to the 8th equals 4 to the, in this case, we're going to add the 6 and the 8. So it's going to be 4 to the 14th power. So we could rewrite it as 4 to the 14th. And we can only do that when the bases are the same. 12 to the 6th times 12 to the 3rd. The base stays the same. We're going to add the exponent, so it's going to be to the 9th power. So it'll be 12 to the 9th. And we're going to divide here. Anytime we're dividing, we're going to subtract those exponents. So 5 to the 10th divided by 5 to the 3rd. Okay, our bases are the same, so we can do it. 10 take away 3 is 7. So that would be 5 to the 7th power. Someone in class asked me about, oh, I really didn't need to put 7th there. Someone in class asked me, what if I had this, 5 to the 3rd over 5 to the 10th? It would be the same thing. So it would be 5 to the 3 minus 10, which would be 5 to the negative 7. Now, we never keep a negative exponent. We're going to talk about that in just a minute, but it does work the same way. 7 to the 6th divided by 7 to the 3rd is 7 to the 3rd power. Any number raised to the power of 0 is going to actually equal the number 1. Okay. A to the negative m, we don't like negative exponents, like I said here. So we're going to rewrite it as a reciprocal. And anytime we change this to the reciprocal, in other words, you flip the fraction, the exponent changes signs. And our last one here is power to a power rule. So 15 to the 6th to the 7th really means 15 to the 6th times 15 to the 6th times 15 to the 6th 7 times, right? Which really means 15 to the 6 plus 6 plus 6 plus 6 7 times is 42. So the shortcut here is to multiply those values. Okay, so that's the same thing as 15 to the 42nd power. Okay, so let's actually talk about these exponent rules. So if you're multiplying bases, right, same base, different exponents, you're going to add those exponents. Dividing, same base, different exponents, you're going to subtract the exponents. Any number to the 0 power is 1. And anytime you do a power to a power, you multiply the exponents. A to the negative m, we can write it as the reciprocal. So remember, that's really a whole number over 1. So that becomes 1 over a to the positive m. Same thing here. If we have 1 over a to the negative m, if we have a negative, we're just going to do the reciprocal of this fraction, and it's going to make that exponent positive. We can also break apart multiplication and division. So a times b to the n power is the same thing as doing each one individually. So a to the n times b to the n. And the same thing with division. So a divided by b to the n power can be rewritten as a to the n divided by b to the n. Okay, so we're going to now talk about functions where the variable is the exponent. These are called exponential functions. Okay. So it's an exponential function. What this means is that every time x increases by 1, the value of the function increases by that amount. So it's going to triple, or by 3 times. Okay. So our y value triples as our x value increases by 1. And so we're going to look at 2 functions now. Okay. So the first one here is going to be the function f of x equals a to the x. Okay, well, I guess it's one function, but our a values are going to be different. So in this first one, we're looking at a is greater than 1. So here's the graph of a is greater than 1. You're going to want to write this down and remember this. Okay. So when a is greater than 1, the graph of the function increases exponentially to the right. Okay, so it's increasing to the right. And the larger the A value, the steeper the slope. So in other words, the faster it's going to increase. This is our graph when A is less than 1. So when A is less than 1, the graph of the function increases exponentially to the left. And the smaller the A value, the steeper the slope. So no matter what the value of A is, these graphs will always pass through the point 0, 1. So this graph and this graph will always pass through the point 0, 1 for the parent function. Okay, keep in mind that we are going to be changing this and transforming this just like we do any other function. So our domain of our function, so how far to the left do each of these graphs go and how far to the right? They go from negative infinity to positive infinity. Okay, sorry about that. So the domain of the function is negative infinity to positive infinity. So it goes all the way from the left and it continues all the way to the right. However, if you'll notice the range of both of these functions, okay, they don't ever cross the 0, okay, or the x-axis. So our range is actually going to be 0 to infinity, and they never actually touch the x-axis either. So we're going to make sure we have a parenthesis there instead of a bracket. The graph of the function will get very close to the x-axis, as I just said, but it's never actually going to reach it. So that's actually called an asymptote, and you guys have seen that word before, okay, but now you're seeing it again, okay? So an asymptote, meaning it gets really, really super close, but it never actually touches it. And let's go on ahead and look at descriptions of these transformations. So same thing as usual. If the number is by itself after, okay, it's going to be shifting vertically. If it's with the x, it's going to be shifting horizontally, and it's always opposite of the way it looks. Okay. So here, 5x plus 3, that means it's going to move up 3. 9 to the x power minus 2, that means it's going to move down 2. Here, that plus 4 is with the x, that means it moves left 4. And 8x minus 1, that means it moves right 1. So our domain and ranges, let's take a look. So what happens to our domain on these two? Okay. So our domains don't change at all because our domains are always negative infinity to positive infinity, or all real numbers, right? So that's our domains. Okay, but our ranges are going to change. Okay? Our range of our parent function is from 0 to infinity for both of these. Okay? So now if we're shifting this whole function up 1, our new range is going to be 1 to infinity. For this one, if we're shifting this whole thing down 6, our new range is going to be negative 6 to infinity. Now let's take a look at these two. So our domain, no matter what we do, is going to be all real numbers or negative infinity to infinity. I don't know why I keep swapping back and forth. Okay, just to remind you guys, I guess. And our range. So did we change from the parent function? Did we shift up or down any? No, we did not. So this is going to be 0 to infinity, our range for both of these. So it's really important that you pay close attention to that. Exponential functions are used all the time in everyday life, especially when you're talking about credit cards and banking and things like that. So simple interest. So simple interest means, hey, I have a savings account I just opened, and every month I'm going to put some money in it. Okay. And that is the only money that is going to be in my account. Okay. So we call that linear growth, and that's assuming that the amount is the same every month. However, credit cards, buying a house, buying a car, putting money in savings accounts, CDs, mutual funds, okay, that is an exponential growth. In other words, if you start working when you're 18, you get a full-time job, and you say, well, My first paycheck, I'm going to put $5 in. So I start at 0 and I put $5 in. You don't ever have to put any other money into that account again. It's going to automatically continue to rise every year exponentially. It may, or every quarter usually, but it's going to continue to increase because it's taking into account the money that's already in there, and then it's adding the interest for however long it's been. So that is exponential. So when you guys hit retirement, or you're 18 and you're thinking about, well, you won't be thinking about retirement anyways, but even $5 a paycheck is going to make a huge difference. It doesn't make such a huge difference if you're 45 and you start putting money in, because it's not going to have as long to grow. You want your money for retirement to grow as long as possible, because then the exponential rate gets bigger and bigger, and it's going to get faster and faster. So, and that's the same with, car payments, house payments, credit card payments. Okay, that is exponential growth, the interest that you're paying them. Okay, so it's really important that you guys understand exponential growth. And if you do nothing else in your life, in your math life, after pre-calculus or algebra 2 or whatever class, you should take a finance class, okay? Because it is going to help you immensely. Okay, so compound interest, we have a formula. Okay, it's going to be our amount equals our principal. That's our initial amount that we put in, times 1 plus our rate to the end. So our rate is going to be given to us as a percent, but we use it as a decimal. Okay, so when we're putting it in our formula, we need to change it to a decimal. And then N is the amount of time, and that depends. Credit cards are monthly. Some dividends are quarterly, so every 3 months. Okay, so it depends. Sometimes it's yearly. Okay, but that N makes a difference. Okay, and if you want to see, hey, how long is it going to take to get to 5,000? Then you could easily graph whatever you have here and graph this 5,000, right? So say I put $5 in an account that is at 1% interest, and I want to see how many years it's going to take me to get to not 5 to 5,000. Okay? Then I could go ahead and I could graph that. So I'm going to say, hey, 5,000 is what I'm trying to get to. Okay, so I'm going to put that in my Y2. Now in my Y1, I'm going to put this formula here, which is 5 times 1.01 to the X, or N power. Okay, and I'm going to see where these lines intersect. Okay, so my graph is all weird right now. So I'm going to set my window. I know that my Y minimum, we'll set it at about 4,500, and we'll set my Y maximum at 5,500. Okay, my X minimum, I'm not going to start until year 0, and I'm going to go, I don't know, I'll go to 150, and I'll choose 5 or maybe even 10-year increments. Okay, I'm just trying to get it so I can see the graph. Okay, so it looks like I see part of the graph. Okay, I don't see it all, but let's go on ahead and see if we can calculate this. So I'm going to go to second trace to calculate, and I'm going to calculate the intersection. So there's 2 graphs on there, so it's going to ask, hey, is this my first curve? It's somewhere, I don't know where it is, but it's found it. My calculator's found it, so I'm going to hit yes. Is this my second curve? Yes. Okay, and do I want it to guess? Yes. Okay, so now it's going to give me a guess of how many years. And I must have inputted 5 times 1.01 to the X power. Did I? So, yes, yes. So I must have input my, Yep. Okay, so here I'm going to need to put parentheses. So to the x power. There we go. Now we should, oh, no, now it's telling me there's an error. Oh, because I used a bracket instead of a parenthesis that time. All right, so now let's see what happens. Sometimes these things are finicky. All right, so second calculate. Let's see if we can find our intersection now. Hopefully it works this time. I just made this one up, so yeah. So I just made this one up, so possibly, you know, there's something going on with my graph here, with my original that I made up, okay? Because if there's 5 times 1.01 to the n power, there should be another graph on here, but it looks like somewhere I've made a mistake when I came up with this formula or this equation, okay? So regardless, if you want to find where it's going to cross, you know, that is definitely doable. And perhaps it's going to take too many years. Maybe, you know, maybe my X window wasn't long enough. Maybe if I did 1,000, you know, then that would work. So you kind of, sometimes you have to kind of play with this and see, you know, where is it going to touch? Where is it going to hit? But it's really easy, you know, especially if you're given something like on the worksheet or in your, you know, Apex quiz, then you can plug those in and see where they intersect. Okay, so your calculator really does come in handy when you're working on this. Okay? All right, so you guys, that's it for today. Have a great day. If you're in class, if you were in class, do the worksheet. Otherwise, you need to do the Apex quiz.